Hi, everyone. Today's webinar is a short presentation on importance of system approach in selecting and sizing centrifugal pumps. We only have 30-40 minutes to cover the subjects. Therefore, we are only focusing on centrifugal pumps and their hydraulic interaction with connected pipework. But as you will see in the next slides, the definition of pumping system is so wide, and to discuss all aspects of pump system relationship and other pump types, we need much longer session, which I hope we can cover those in future webinars. So throughout the webinar, when I refer to pump, I mean centrifugal pump, and when I refer to system, I mean piping system. Agenda for today's webinar, we briefly explain what system and system approach means. Then, as we are going to focus on hydraulic interaction between pump and piping system, I will briefly explain the characteristics of piping network, which we call it system resistance curve. Then we briefly review the characteristics of a centrifugal pump by reviewing its performance curve. And then we review how pump and system are going to interact with each other in different operating scenarios. Particularly, we want to see how unstable pump can operate steadily by proper system selection. We conclude the webinar by a case study, and then we move to Q&A session at the end. So, what is system approach? Some pump users may think that just by having set of hydraulic requirements like head and flow rate and defined set of fluid properties, a pump can be selected and put into service. Sometimes this is all you need, but more often you need much more details to select the proper pump to meet the system requirements. Some operators may just look at capital costs, while others are more conscious of efficiency, reliability, availability. But regardless of which aspect is more important to you as a pump engineer, you should always remember that every pump is part of a system working in an optimal way. It will work in an optimal way only if all the components are well tuned. So to find the best economical and technical solution for your pumping need, the plant and the pump should be seen and optimized as an entity. Therefore, it is necessary for making a good pump selection to know how those plant features will have an impact on operation of the pump. So all these parameters, variables, components, which directly or indirectly impact the performance and reliability of the pump, we call them pumping system. Just to name a few, for example, connected pipework, which is the focus of today's webinar, condition of suction and discharge points in terms of pressure, height, temperature, the physical height differences between pump and, for example, suction reservoir or delivery point. Environmental conditions can be considered as system parameters, fluid properties, and criticality of the service. These are just very few of the parameters that you probably need to be mindful of when selecting the pump, but there are many publications that contain much more comprehensive list of system parameters. But if I want to highlight the most important takeaway message from today's webinar, it would be that pump should never be seen in isolation. Not appreciating the interface between pump and system can sometimes end up in an expensive mistake. To see the impact of some of these system parameters on pump, I've listed just 3 of them here. For example, by changing the temperature, the pumping temperature, the physical properties of the liquid will change, and consequently the frictional loss delta P across the pump and MPSH available will change. The next one on the list, for example, is pipe lengths. The number of piping components, for example, number of bands, valves in the system. If we change those, then that will change the pressure loss, and that will influence the velocity profile in the system. As a result, the suction pressure, hydraulic performance, MPSH available, all will be impacted. The criticality of the service is an interesting one because it will dictate the sparing philosophy for your system. For example, whether you need 200% pump or 350% pump. It can also influence the pump type, which it will impact the system hydraulic. For example, whether you have 2 pumps running in parallel or 3 pumps running in parallel. It will also have impact on power requirements. So let's focus on the piping system and system resistance curve. System resistance curve essentially is a head or pressure loss curve versus flow rate. As we know, pressure loss in a pipe is a function of the square of liquid velocity, which the most commonly used formula for calculating friction head loss in a pipe is a Darcy-Weisbach formula, which you can see here on this slide. F in this formula is friction factor, which can be found using Woody chart. L is pipe length, V is mean velocity, D and G are internal pipe diameter and acceleration of gravity. To calculate the total friction loss in a system, for example, from fixed point A at suction to fixed point B at discharge, system should be broken down into individual sections. First, the straight pipe lengths all will be added together. Then other components in the system like bends, fittings, valves, they can be modeled in equivalent straight pipe lengths. There are some published tables, all based on experiment, which will detail the equivalent straight pipe lengths for individual components. For example, a pressure loss in a short radius bend is equivalent to 30 to 35 D or diameter of the pipe, or medium radius bend is 15 to 20 D. There are other methods to model the equivalent pressure loss in components, such as using the resistance coefficient curve or flow coefficient, but probably the easiest one is the straight pipe lengths. So once all the components been modeled in the equivalent straight pipe lengths, all will be added together. And then using this Darcy-Weisbach formula, we can calculate the friction loss in the system. System resistance curve then technically is a formula which can be represented in a quadratic function of flow rate, and this formula has 2 parts. The first part is the frictional head loss, which can be calculated using the Darcy formula, and the second part, which I showed it as a H static here, is the term which is independent of flow rate. For example, when delivery point is vessel with constant pressure, it is independent of flow rate in the system. Or, for example, any elevational differences between suction and discharge points, again, that's independent of flow rate. But friction loss is a velocity or flow rate dependent. The reason that we show the system curve in head, or say meter water, against kind of flow rate is because the pump performance curve also will be shown as in meter water. So it would be easier to compare these two together and discuss it in the next slide. System resistance curve can change. In fact, any factor which can change the frictional or static head loss consequently will change the curve. For example, throttling the control valve changes the friction loss. And in this figure, you can see the impact of throttling based on opening percentage of the curve. By closing the valve, curve will become steeper. Some other factors that can change the curve, for example, are if suction and delivery point of the system if they have variable liquid levels, then a static head part of the curve is changing. For example, when you're pumping a liquid from tank A to tank B, both tanks are open to atmosphere. Liquid level in tank A is dropping, while liquid level in tank B is increasing. This means while pump is working, suction pressure is reducing and discharge pressure is increasing. So static head part of the system curve is changing continuously throughout the pumping. Change in delivery pressure also has the same effect as change in liquid level at suction and discharge. Or for example, if fluid properties are changing, for example, changing the temperature, it can also change the friction loss because density will change and consequently the frictional head loss part of the curve will changing. Change in friction factor, for example, as a result of fouling or aging of the system can also change the friction head loss. So as you can see, not necessarily the curve will be fixed throughout the operational life cycle of the pump. So now that we briefly reviewed the system curve, let's now move to pump performance curve. Performance curve can be shown as quadratic or second order polynomial function of flow rate. In some publications, you may see third order or even higher degree polynomial curve fit, but second order seems to be accurate enough. The curve shape for a given centrifugal pump is mainly a function of the impeller specific speed. Lower the specific speed of the impeller, the curve is flatter. In other words, high head, low flow pumps will have flatter curves than high capacity, low head pumps. Curve is also a function of number of vanes. More vanes means flatter curve. There are some points on this curve that we need to be familiar with, which I've listed them here. For example, shut-off point is where pump generates highest head but at zero flow rate. This is when pump is running against closed discharge valve. End of curve, for example, is the point that pump generates highest flow rate and lowest head. When pump start against, for example, empty discharge pipe with open discharge valve, normally pump will need the highest power and will need the highest MPSH required at this point. The pump's best efficiency point, BEP, is generally near the middle of the curve. Pump will have the highest efficiency and life expectancy when it runs at or near the BEP. You can see, for example, curve number 3 in this figure, which is a reliability for the pump, showing that the reliability is maximum when pump is running at BEP. Typically, the area on the curve between 70 and 120% of BEP is known as the preferred operating region for the pump. There is a wider operating region for the pump. We call it allowable operating region, which is set by the manufacturer. Some factors defining allowable operating region are temperature rise, bearing life, vibration, noise, MPSH margin. Then we have minimum continuous thermal flow, which is defined by temperature rise. This is where the efficiency is low, which most of the exerted power turns into the thermal energy rather than head. We have minimum continuous stable flow, which is defined by acceptable vibration limits. The figure in this slide is from ISO 14414, which shows some possible side effects or consequences when you're not running at or near BEP. Here you can see a typical unstable curve. An unstable pump curve is a performance curve that does not continually rising when you're moving from the best efficiency point back to shut-off. In fact, the curve reaches a high point before reaching the zero flow. A pump with an unstable curve has potential to experience head and flow fluctuations when operating in certain regions. This can cause instability, therefore we call it unstable curve. We will explain in next slides how this leads to instability. Another way to identify if curve is stable or not is to draw a fixed headlines, which is a red line in this figure. And if these red lines, for example, intersect with performance curve in more than one point, you can call the curve unstable. Many industry standards and end users, they require that the head should continuously rise from the rated condition point to shut-off point. And there are some references to this type of curve as a stable curve. And also it is common to state the minimum acceptable increase in the curve, which is normally 8% for a single pump and 10% for a pump running in parallel. Having said that, it doesn't mean that pumps with unstable curve should be ignored. In fact, pumps with unstable curve, generally they have higher efficiency than other pumps. As long as you tune your pump and system carefully, unstable pumps can be used. I personally have seen several installations with unstable pumps curve, which were in service for many years without any issue, any problem. This will highlight the importance of system approach when selecting the pump, that by carefully tuning pump and system, even pump with unstable curves can operate without any problem. So let's see how pump and system will interact. Centrifugal pumps are so simple in terms of operation. They simply operate at intersection between system curve and pump performance curve. Therefore, their operating point is somehow dictated by system curve. If intersection point is near BEP, then pump operates at its best kind of point with the lowest vibration. And it is fair to say that manufacturers normally design each centrifugal pump with a given impeller and given operating speed for only one single operating point, and that's BEP, because there is only one BEP on each curve. All other points that we explained before, such as allowable or preferred operating regions, there are somehow compromises which should be carefully considered when sizing a pump. Selecting a pump with an operating point at or near the left side of the BEP is a common practice. It is a conservative type decision, but do not be afraid of running at right side of the BEP point. If the operating points are not too far to the right, there will still be plenty of margin before the end of curve. Selecting a pump near the BEP will result in most efficient pumping with the least amount of vibration and radial forces on the shaft. So as long as it's not near the end of curve, operator might decide to run on the right side of BEP as well. But if it is so far right or very close to the end of curve, because MPSH increase, there will be MPSH required by the pump will increase. There will be higher risk of cavitation. So all centrifugal pumps are subject to internal recirculation in both suction and discharge of the impeller when they are operating away from BEP. It is surprising to know that underperforming of pump is a widespread issue in industry. I was reading an article a couple months ago, which several years ago, I believe, a technical research center in Finland, they evaluated around 1,700 pumps, which were installed across 20 different process plants. they found that the average pumping efficiency was below 40%, and that over 10% of those pumps, they were running below 10% of efficiency. So unfortunately, the poor pump system selection is still a widespread issue. So do not run near or at the end of care. There's a risk of recirculation, cavitation, NPSH margin issue. And also, I would suggest do not run continuously near the minimum flow limits. As a general rule, do not select a pump with the maximum or minimum size impeller. Selecting a maximum or minimum impeller, it will leave no margin for mistakes in your calculations. So you cannot change the impeller with a slightly bigger or smaller one if and when needed. Many users may specify impellers that are less than the maximum diameter impeller, but at the same time, they are sizing the driver for maximum impeller at end of care. Nowadays, this approach is not the best practice because it will result in oversized motor. And it would be interesting to know that the minimum impellers are less efficient than larger impellers for a given pump. So here we have an unstable pump A, which we are going to use in two different systems. System 1 is mainly governed by friction loss, and system 2 is mainly governed by static head. These are typical curves, and they've been exaggerated to highlight the discussion point. A resistant curve with mostly friction components, which is system 1 in this figure, but little static pressure head will intersect the pump curve at a higher angle than a curve with mostly static head, but little friction loss. Because normally the curves with mostly friction components are steeper. So assume that we want to start this pump in each system. Discharge valve is closed, so pump is starting against the closed valve from shut-off point. On starting the pump, duty point of each system is obtained by adjustment of the discharge throttle valve, which is at a fully closed position when you start the pump, and will be opened gradually to shift the operating point to the designed duty point, which is the intersection between the pump curve and the system curve. What throttle valve is doing in effect is dissipating the head differences between what pump is generating and what system needs. And at intersection, assuming the control valve of the throttle valve is sized properly, the valve will be either fully or mainly open. The head differences between the curves are shown as H1 and H2 on this figure. So system 1, the difference between the pump curve and system curve is continuously decreasing, which means the valve is continuously opening. So operator is experiencing a smooth startup, hopefully. System 2, on the other hand, the differences between the pump generated head and system loss is first increasing, and once passes the hump, it decreases continuously, same as system 1. So throttle valve for system 2 has to be tuned to match the system. That means valve needs to open slightly to a certain amount and then slightly close and open again. If you remember, we discussed that in the previous slide, that unstable curves, they're likely to cause instability. Here, probably you can see why. In system 2, if we continuously open the discharge valve, similar to what we did in system 1, once pump reaches the peak in pressure loss, it cannot generate the head that system needs. So it is falling back to shut off. But because the discharge valve is opening, pump again tries to generate more flow rate, but reaches the hump, cannot pass, and again falls back to shut off. And then you have this cyclic kind of behavior in the pump head. Having said that, by knowing how pump is going to interact with system, we can tune the startup sequence and adjust the throttle valve to push the pump over the peak point and toward the rated point. So by knowing how pump and system interact with each other, you can effectively use an unstable pump in your system. Therefore, it is fair to say that no pump is unstable. Its application in a system will decide whether it's stable or unstable. A user, for example, in system 1 probably doesn't even notice that he's using a pump with unstable curve. And if we tune the startup sequence for system 2, we can still use the unstable pump in system 2. This startup scenario, which we just explained, it can be a lot more complex if you start two unstable pumps in parallel. In a previous slide, we saw how an unstable pump can be started in stable conditions. Here we are going to explain that once a pump is in service, change in system curve may push the pump towards instability. Here again, we have an unstable pump A, which we just started in the previous slide, and a system with a variable system curve. We explained before that the system curve can change throughout the operation because of several factors. One of the factors is a variable static head at suction and discharge of the pump. By transferring liquid from tank in suction to tank in discharge at constant flow rate, the suction static pressure is decreasing and discharge static pressure is increasing. So at the start, the combination of pump and system curve could be seen, say, as stable, but after a while, the intersection point between the system curve and performance curve, it moves to the left-hand side of the hump, and as soon as the system head increases to maximum pump head, pump no longer can provide necessary head and likely to fall into that cyclic variation in head and flow rate. We know that for a constant speed pump, the head developed by a centrifugal pump, it varies with the capacity. So higher the capacity results in the lower head. So for example, here, once the intersection point is moving towards the left-hand side of the hump, pump tends to move towards no flow point, which in turn flow rate reduces and resistance of the system decrease, which then encourages pump to deliver more flow rate, but then more flow rate means less head, so pump cannot generate the head, and that cyclic kind of behavior will repeat itself. Such conditions that we just explained are more likely to happen when a system has free liquid surfaces at suction and discharge. Therefore, it is very important to operate a pump with a stable curve in these conditions. Pumps can often operate in parallel or series to satisfy system needs. For series operation at a given flow rate, head will be combined, and now a new pump curve can be generated for series configuration. For parallel operation at a given head, flow rates will be combined. Generally, more pumps in parallel, the less efficiency system has. This means flow rates of two identical pumps in parallel is less than twice the flow rate of single pump. One of the disadvantages of series operation is that if one of the pumps fail, the combined arrangement cannot work. Therefore, when you're considering series operation, make sure reliability and availability of the system will be taken into account. Parallel operation can provide better flexibility in terms of availability, So it depends on number of parallel pumps in service. If you lose one of them, the other pumps can still deliver. It's important to remember that parallel pumps, they're better to have identical performance curves. I'm saying better because it's not necessary, and I have seen non-identical pumps in parallel operations, but it needs careful analysis of the system interaction, specifically during the transient startup and startup and stop sequences. So sometimes it's just easier to just have identical pumps, because if one of them generates more head than others, it will push the other pumps back in their curves towards the shutoff. API 610 is asking for 10% head rise from rated to shutoff for parallel operation. So here we reviewed some scenarios of pump system interaction, which hopefully you found useful. And sorry if I was talking a little bit kind of fast. We had lots to cover in this short period of time. Now we move to a case study, which I've had recently, but what I'm going to do, I will explain the problem that we have with these NGL pumps at one of our sites, and I will provide you with some facts and data. But then I would like you to use the discussions that we had in this webinar to identify the issues, or say pinpoint the problem that we may have with these NGL pumps. We can then use the Q&A session to share ideas and discuss the case. And at the end of Q&A session, I will explain what the problem is with this pump. So here we have two identical NGL pumps, but one of them has a different performance, or underperforming compared to other one. These two NGL pumps are identical, at least based on data sheet and manufacturing drawings that we have. Pumps are receiving NGL from a vessel and discharging it to an export pipeline. The issue that we have here is that pump A, which you can see it on the photo on the left, it has higher power consumption compared to pump B. And the difference is considerable. It's almost 90 kilowatts higher than the pump B. Also, pump A is experiencing higher bearing temperature compared to other pumps. So here are the facts, which probably you will need to identify the issue or root cause. Liquid is NGL, which means it has higher, very high vapor pressure. Pump A, the problematic pump, has much higher running hours compared to pump B. It's more than twice. That was the main pump in service since commissioning. Arrangement is 200%, so only one of the pumps is in service at a time, which means the pumps are not running in parallel. Vibration levels on both pumps are well within the limits, but suction and discharge pipe routes are not exactly identical. Pump A has a couple of more bends in suction compared to pump B. So based on the conversations that we had in the webinar regarding the pump and system interaction, if you can tell me what would be the possible root cause for this underperformance of pump A. Okay, hope you found this webinar and the subject useful. Now we move to Q&A session, where I would be happy to answer your questions. Thank you. Okay. As we are waiting for some of these questions to come in, there are a couple of kind of factors, system factors, which even though they are very, very important, but unfortunately we didn't have time to go through and discuss those in today's kind of webinar. One of them is MPSH, which I believe it deserves its kind of own session to be discussed that in more detail. In particular, how system will influence the MPSH or define the MPSH available, and how MPSH required can actually influence the selection of the pump. So hopefully we can cover those in future kind of webinars. I believe if you look at some of the kind of publications on the subject, you will see the impact of MPSH on pump selection and suction specific speed and specific speed of the impeller, which will dictate the construction of the pump. Lower MPSH means higher suction specific speed, means larger impeller eye, and it will result in narrower operating region for the pump. The other subject, which I think it's also very important to be discussed in more detail, is cavitation. And to be honest, it would be very important to remember that not necessarily as long as you have higher MPSH available than any MPSH required, then it means you don't have any cavitation in the system. Sometimes you need to have more than 10 times or 15 times MPSH required available to technically have a cavitation-free operation. There is a very informative kind of article written by Bruno Sciovolo, which I use regularly. He's from Floser and another gentleman, which I cannot remember the name. I can share it, to be honest, after the session, and you can find it online. It's free to download. That's a very informative kind of article on importance of MPSH and MPSH margin, and also the cavitation, which I would encourage you to read. Okay. Yeah, we are receiving some questions. I'm just going through some of those. One of them is please explain a bit on system and pump care. As we discussed, I mean the system care and pump care, they will interact in a single point, and the whole kind of also proper kind of pump selection is to select a pump which that intersection is as close as possible to the best efficiency of the pump. This is in a nutshell. The other one is in regard to reliability, what is the operating range allowable of performance from the BEP of the pump? What I would suggest for that is to go back to that ISO standard, which I referred to into presentation. That will define, and also API 610, that will give you good kind of indication. But in general, there is no kind of hard and fast rule in terms of what is the allowable operating region or what is the preferred operating region for the pump. It depends. When the suppliers, they have different criteria, but most important thing to remember is actually paying attention to the BEP or best efficiency point on the curve. The other one, Yeah, I will definitely share the publication reference for that cavitation article. Okay, I should have the detail here somewhere. Yeah, the title is Pump Cavitation, Various MPSH-R Criteria, MPSH-A Margins, and Impeller Life Expectancy. It's written by Bruno Schiovalo and Frank C. Weiser. Both of them are from Flowser. As I said, you can find that publication free to download on the internet. The other question is, has performance of pump A declined over time, possibly due to wear cavitation, always been underperforming, have the extra condition? Okay, one of the gentlemen actually is suggesting a root cause for the underperforming of the pump A. The pump A, I think it was always underperforming from day one. It is in service for more than, I think, 25 or 30 years. But this underperformance been highlighted recently because of this kind of continuous maintenance routine that we are doing on the pump. So I cannot say by definite that the pump A was always underperforming, but at least for the last 10, 15 years, I would say yes, it was highlighted as an underperformer, kind of, or bad character in the system. Lots of questions on whether slides will be available after the presentation. Yes, I believe you will receive a link to the slides and they will be available after the presentation. Okay, let's go back to the case study and the issue that we had with that kind of bad actor, pump A. The reason that the pump A is underperforming is because the pump A has a slightly different system curve compared to pump B, because obviously the geometry of the suction and discharge of both pumps are not exactly identical. Pump A has some more components in the suction. So as a result, the system curve for pump A, technically, will intersect with the pump curve probably in a different point compared to pump B. When I say different point, probably it would be closer to, on the left-hand side of the BEP, or closer to the minimum continuous flow. Pump A had much higher operating hours compared to pump B, so it is very obvious that there would be, if there was a risk of suction recirculation, pump A would had kind of was exposed to more kind of operating hours, so as a result there would be more wear and tear in the pump. That will cause internal wear rings to wear off, so compared to pump B, because it was in service more, and it resulted in higher internal clearances. This then resulted in the lower performance of the pump A compared to pump B, and as a result means when the performance is lower, it means higher power consumption is technically required to deliver the same pressure compared to the next pump. Cavitation, we looked at the cavitation risk pump A, but when we looked at the vibration signatures on pump A wasn't actually cavitating at the time of measuring the vibration. But it doesn't mean that, for example, in the past, pump A wasn't subject to any kind of cavitation. But definitely suction or discharge recirculation, because the intersection point between the system curve and the pump, they were not so very close to the best efficiency point. They could be actually seen as a suspect that caused more internal wear for pump A, and as a result, lower performance for the pump A. So I can see that some of you reference to some root causes for this, which is in line with that, with what I explained. So I think, yeah, you were paying attention to what we discussed in today's webinar. Okay, I would like to thank all of you for your time and your attention. Hopefully, you'll find the subject useful and relevant to what you are doing. And as I said, the slides will be available after the webinar to share and to reference. And also, I will try to, even though I mentioned that the reference to that article, I will try to find a way to share it with you after the webinar as well. But as I said, that publication, that article can be available free to download over internet. Okay, thank you very much, and hope you enjoyed the session.